So today I would like to present you the third part of our series about the endoplasmic reticulum revealed by data modeling of super resolution single particle trajectories. And today we will use another tool, which is a theory about diffusion in network or in graph. I would like to remind you that most of our lectures are summarized on our website www.bionumeric.org. Then it's working to slide number 4. So the endoplasmic reticulum, as we have seen in these two previous lectures, is divided into two parts. One is the rough endoplasmic reticulum, which we haven't discussed much so far, and the smooth one, where we use single particle trajectory to better understand what is the flow inside this tubule that I have shown here through this arrow, where you see here an example of a tubule that is connecting two neighboring nodes. So for that, we use single particle trajectories. So this was experiments done by my collaborator, Edward Avezov from University of Cambridge. And what we did together is to look at the specific trajectories and color them, not according to each trajectory we attributed a color, but according to the displacement that is shown here. So what is the displacement? We calculated the quantity xt plus delta t minus xt and plotted the histogram. This was done in collaboration with him and my student Pierre Parutto, where what we did is we looked at region where this quantity is small, and we looked also at region where this quantity was large. This is in red. And what we saw is that region of low density in blue are connected here, for example, by this large jump. And this led us to the conclusion that large jumps is the mode of transport between the nodes located here in blue. 4 and 5. So then, to better understand the nodes and that we characterize here as junction, we applied an algorithm called the DBscan algorithm that clusters points that fall into a close proximity. And so we use this to label this region, and we fit them with ellipses that defined these clusters. So once this region have been defined, so you can use, go to Google it, you can see what the DBscan algorithm is, and it's really a useful tool. Once we define this region here with this blank ellipse, we could then study what happened between the ellipses. So before doing this, I would like to remind you that this is how trajectory were first acquired. So let me zoom more specifically on this example, where you see here trajectory are not colored according to the velocity. So the region of high density are shown here by these ellipses. And with these ellipses, what we plotted is the region of high density. That is, if we looked at the number of points that is falling, for example, in this region here, you can see in red the region containing a lot of points, so according to the color code that is represented here. And then for each region, we could then estimate the diffusion map by calculating in each pixel the diffusion coefficient that we have discussed in the previous movies. And the last part, which is concerning this YouTube of today, is to understand how this region of high density are connected. So we saw that red, when we had these two regions, we saw that we had this red big jump that corresponds to really fast jumps of the velocity. And so here what we did is we decided to color code them according to two possibilities. One is unidirectional and the second one is bidirectional. That is, when we count a trajectory that goes from A to B, suppose here we have 1, 2, and 3 trajectory that goes from A to B, and one that goes from B to A. Then we could write the ratio, for example, the trajectory, the number of we define, let's say, the flux from A to B. This was 3, and then what we could estimate is the ratio of the one coming from A to B to the total flux, that is the number of trajectory that went from A to B plus the number of trajectory that went from B to A. And if this ratio was above a certain threshold T, we say that then the direction between the two nodes is unidirectional. Otherwise, when it is less than T, we say it is bidirectional. And this is how we built here this graph according to this division, where you see arrows that can be either in red, which indicate the direction, or in blue, which is bidirectional, where the trajectory can go in both directions. All right, so this is, I have already explained this, but let me show you more. Specifically, we calculated the number of trajectory between two nodes. Let's say, for example, here, if this is A and if this is B, we calculated this number, we divided by the total number acquired, of course, during the set of the experiments. And we decided a threshold, for example, 0.75, and say that we attribute a direction or not, depending if this ratio was larger or not than 0.75. And for example, doing this, we could find in this particular ER network that we reconstructed that 87% are actually nodes where the trajectory can go in both directions. Later on, we discussed in the paper that we published in Nature Cell Biology, that I will give the reference toward the end. We show that actually this can happen at a different moment of time. That is, during a certain time, all trajectories they all go into the same direction. And if we wait this, let's say at time t1, but then if we look at the same story at time t2, we found that actually they go in the opposite direction. So this is something that we have discussed in the paper, but we will not discuss that here. So finally, we could ask the question, once we know this mode of motion, and here we will make an assumption that the mode of motion is very fast. So then we can ask the question, how long it takes when you put many particles, many proteins, or many whatever you want to study that are generated at point A inside the network, which is now approximated with a honeybee type network. How long it takes when you start at time 0 at A to arrive in B. And so for this, one possibility could be to directly look at this and to make a simulation inside the ER network. So we have currently developed this possibility, but I would like now to go specifically to the case where we approximated this ER network by this honeybee. And so basically you have now what is called a Brownian motion on graph. You start particle here, it jumps, you wait a certain random time, which could be Poissonian time, and then you decide for a pass and you repeat, and then you generate a pass here, and you look at the first time a particle arrive in A, and you start afresh. And when you average, so for each trajectory you have a time t1. So now suppose we look at another trajectory that I will show now in blue. So you have another one. So you look again at the time for this trajectory and you call it t2. And so once you have all of this trajectory, you average the time for all of them. And this goes what is called the mean first passage time, which is tau. And this is what you're interested in estimating and calculating. So for this, a short summary is that you can approximate this network in the continuum by using the solution of the Fokker-Planck equation. And this operator here is obtained by approximating the diffusion operator on a graph where from one point you can jump to only the 3 neighboring points, as I showed here in green. And then solving the associated Laplace equation, if we take into account that the time in a node can represent the time spent in a tubule plus the time spent in a node, so this is the rate of switching. Lambda is the total rate of switching that accounts for the time in the node plus the time in the tubule. So the rate of switching when you start at 0 and you want to switch to A, B, or C. And so what we found, and again, this is a crude summary, is that the time depends on the size of the network, the rate lambda, and it's independent of any point A and B, as long as A and B have to be, the distance between the 2 points has to be far in, they have to be located far enough, not just in the neighborhood of the initial point, A, for example. So they have to be far enough. 8 and 9. Another interesting aspect that we have studied here is the statistics of the extreme. So suppose you start at point S and you are interested what is the time for the first particle to arrive to point T. And this is a work that we have done with my student Matteo Dora. And so if you have not one particle, but you can have 10, 100, 1,000, and you ask, what's the trajectory of the first one to arrive? So the trajectory in the case of diffusion is actually going to be very close to the geodesic, that is the shortest distance from S to T when you look at the distance on the graph here. So this is what we found. And the approximated time constant, that is the time it takes to arrive at T, is actually proportional to this distance, geodesic distance square. And it depends on the diffusion coefficient or equivalently the rate of switching multiplied by a characteristic distance, so that it is of the units is length square divided by second. And then there is this new element, which is the log of the number of particle. That's so this is n of particle, which is a number that are initially put at point S. So this is an example for 100, 1,000, and 10,000. And you see that the length of the trajectory really concentrate when n increases towards a deterministic value, which is what you see here in yellow, which is the geodesic distance. So the conclusion here was that optimal trajectory concentrates, they really concentrate near the shortest geodesic on the graph. And we found that it takes seconds and not tens of minutes for the flow to reach a given node inside the ER. So that could be a reason of the redundancy of many of the matured protein. And 10, and so we are done. So there is a general theory that we have expanded, which is the first passage time on graph. So you can either study the time to start when starting at point A to reach a point B here, when we start at A. You can do it in the hexagonal lattice here. And of course, the question is, what is the boundary condition that we should put at the boundary of the lattice? So one possibility is to put reflecting. So, and here this is a lattice in case B1 where each point is reflecting. And so, as you can see here, if you start, initially you put particles at point S and you ask how long it takes from S to reach any point. So this is the color code here. And as a function of the distance, you can see that you have a first region where the time is going to be increasing very fast, and then it's going to be more or less stable. And this is very clear here in the case of the periodic lattice. And then there are regions where the time increases drastically. It also corresponds to the time where it's very hard to access. So because they are connected with really few nodes, the time to enter this region can be very long. Okay, and so this gives us an idea of how the network topology can affect the mean first passage time. So to conclude, ER trafficking can be modeled as diffusion in a graph. We could use normal and extreme statistics for this, and I haven't discussed, this would be probably for a next YouTube video. We can also use a switching model on the graph, but as we have found recently that this is really equivalent to a diffusion process. So for those of you who are interested in the literature, this is the first paper that summarized the aspect about the analysis from single particle trajectory, published last year in Nat Cell Biology. And we recently posted a paper on arXiv about this active unidirectional network flow that can generate a certain type of mode in packet. And I thank you for your attention.